Hi everyone. So I'll be presenting the work of our student Gemayel that she did under the supervision of my colleague Elodie Puy-Barrault from LRDE, myself, and Jérémy Vaubaillon from IMCCE. And this work is entitled Detection of Meteors in Shuttered Photography with Artificial Intelligence and Mathematical Morphology. And since this work is actually part of the Cabernet program, I will let Jeremy present the whole project.
Hi again, everyone. So the collaboration with LRD started when we realized how many problems we had with the Cabernet project. So Cabernet stands for Camera for Better Resolution Network, and it's basically 3 cameras in the Pyrenees Mountains. The aim is to get accurate orbits of meteors as usual, and the goal is to find parent bodies, to refine meteoroids orbits, and so on. So at the bottom left, you see the field of view of the 3 cameras intersecting over the Pyrenees Mountains, and on the right, you see one of the cameras attached to a wall at Pic du Midi Observatory during the summertime, and that's what happens sometimes during the winter time. So needless to say that maintenance is hard work, maintenance for the hardware, but also for the software. So here is an example of the image that we get from one camera. So you can see the stars up to magnitude, the 8th magnitude. We take 1 second exposure. We have a field of view of 40 by 27 degrees, and each image is about 22 megabytes. You can clearly see that the background is different from the left-hand side to the right-hand side. Is only because there are 2 registers to read the image, and these can be software corrected, of course. So we perform the acquisition for the whole night, and depending on the summer or the winter, we get in the morning between 400 and 800 gigabytes. So you can see here on the left-hand side, there's a nice meteor, but we get lots of objects in the field of view. And in order to detect the meteors, we also saved reduced sized images, so compressed images, and one image weighs only 2.4 megabytes. All the images are saved in a standard FITS format, are 16-bit for each of them. And here is an example of the full moon that is slightly on the edge of the field of view. And you can see that all the parasite lights basically makes it extremely hard to detect the meteors, or at least it would create a lot of false detections. So in the morning, I wake up and I basically have to manually sort hundreds of images, and I'm getting tired of that. And that's when Guillaume and Elodie and Maya comes in place.
Yes, so the main objective of this project is to detect the position of all meteors within the images that have been acquired during the night, and this for every night of the year. So there's already a routine that is running on IMCC's computers, but it actually generates quite a lot of false alarm events. And the classification, as Jeremy said, is done by hand, which is quite tedious and time-consuming. So our goal was to actually automate the classification by resorting to machine learning. And we also decided to rework the detection pipeline to make it less prone to false alarms. So here is a quick idea of how the detection works. So we're working on the image difference between 2 consecutive frames, and there are actually 2 change detection procedures that are conducted in parallel. One is, well, simple pixel-wise statistical test, and the other one actually relies on mathematical morphology, which is a subfield of image processing that focuses on the shape and contrast of the objects within the image. So that's typical results that we would obtain by the two change detection procedures. On the left-hand side, you have the statistical based result, and on the right-hand side, you have the morphological based result. So as you can see, they're not perfect. Obviously, they'll generate quite a bit of isolated false alarms, but they both get the meteor. And what's important here is that they well complement each other. So what we're going to do is we're going to fuse those two binary maps. We do a bit of post-processing by removing isolated pixels or small groups of pixels, or also objects that do not have an elongated shape, because that's what we're looking for. And there is a final processing step where we reconnect large objects that have been fragmented by the word process. And here is the final detection mask that we will obtain on the previous image. So here is actually what we are going to save from this detection procedure. We're not going to keep the whole image, but only the thumbnail image on the object that has been detected. And that's on this thumbnail image that we're going to work for the subsequent classification. How we're working with three types of events. The first one, the one we're interested in, is a meteor event here. But we can also get satellites, which can be of interest for some applications. And then there is still a lot of false alarm events, which can be, again, because of clouds or the moon or the planes, or as you can see in this example, that's a negative trace of a meteor. And so our goal now is, given a thumbnail image, is to classify it in one of those three categories. So either meteor or satellite or false alarm. So if we want to do some machine learning for this classification, we obviously need some training data. And Maya did create a nice training database by analyzing around 2,000 images from the Cabernet project from 2011 to 2021. And for that, she actually ran the detection procedure on all those images, and then manually classified the detected events in one of the three categories, being either thrash or satellite or meteor. And you can see here the number of samples that we have per category. So she tried to keep the three classes as balanced as possible, but also trying to incorporate within each class as much variability as possible. Here is a sneak peek of the created database. So you can see in green that are kind of the meteors that we want to classify. In red, you have examples of satellite images. And in blue, that's everything else, everything that is a false alarm event. So either we can have here negative trace of a meteor, but we can also have only noise, or something that is due to the movement of a star and so on. So we wonder whether we should tackle this classification issue by deep learning techniques or not. And we actually decided to resort to, let's say, traditional machine learning. The two main reasons are that the thumbnail image that we want to classify do not have the same size, and that can be problematic for some deep learning classification networks. And also, we only have a few hundreds or thousands of training examples in each class, which is actually not that much for big networks such as UNet. So we decided to go with traditional machine learning with uncrafted features. And we decided to work with the random forest classifier because it's actually really easy to use. There is no obscure parameter to tune to make it work. And it also gives highly competitive results, provided that we feed it with meaningful features. So the trick now is to define those meaningful features. And so I'm going to present the one we have defined. There are 11 of them, which are either extracted on the whole thumbnail image or on a masked version of the image, where the mask is the one that we got at the detection step. For the features that are defined on the whole image, they are mainly based on the histogram of the image. And the reason is, well, because if we have a satellite image here, we expect the positive trace to be roughly the same size as the negative trace. And so to get an histogram, that should be more or less centered around 0. But if we have a meteor, we should have lots of bright pixels. And so an histogram that should be skewed to the right. Regarding the features defined on the masked object, we again define some features based on the pixel intensity values, such as the average, the standard deviation, and the min and the max values within the mask. But here we also define some morphological features, such as the area of the object, the eccentricity of the object, or the length of the semi-major axis. I'm not going into the details here, but we have a way with the random forest to assess the importance of each feature for the classification. And here is the distribution of importance that we get for the features I just presented. And what's important to remark here is that the distribution is somewhat well balanced, or put differently, there is no feature that appear totally useless for the classification, which is quite reassuring. So for the classification results, we did a stratify 80-20 train test split on the database that I previously presented. And we got over 98% of classification accuracy. So we actually repeated this experiment several times. So we did cross-validation. And while in average, we always got around 98% of classification accuracy with a standard deviation that was a bit below 1%, which means that we consistently get over 97% of classification accuracy. So the random forest classifier with the defined features does quite an awesome job here in the meteor classification. And we also had a look at the samples for which the classifier has at least a 90% confidence in its classification. And in that case, the accuracy goes up to, well, almost 100%. More specifically, the only mistakes that are made in that case are between the trash class and the satellite class, which means that when the classifier is confident on the prediction, it never makes any mistake when it's a meteor to be classified, which is again quite a good news for our method. So what's next? Well, there is still a bit missing here. So the whole detection and classification pipeline is done, but then what we would like to do is to get an accurate centroid estimation of the meteor blobs to recover the velocity. So what's next? Well, first we shall do that. And then we'll have to optimize a bit the detection pipeline, because for now, it runs slower than the acquisition rate. So it's not able to run in real time, but hopefully one day it will. And then we just have to, well, deploy on the Kubernetes computers and hopefully save Jeremy a lot of time. So that's all.